All right, I think we'll get started. So we have a regular week this week. You've got PLAs, you've got homework. I hope you enjoyed your Friday snow day. Skiing wasn't even very good, so it wasn't a great snow day for me. But anyway, usual week coming up the next couple weeks. So you could take a look at the syllabus. We have a couple homeworks, a few PLAs, and then we have another exam before spring break. So yeah, and now we've done everything and all the format stuff that we're going to do in the class for assignments. So you know what to expect for exams, you know what to expect for PLAs, you know what to expect for homework. So if something didn't go right in section 1, if you're unsure about something, this week is the week to sort it out, because I'm probably not going to change what I'm doing unless I hear that something is not working, right? So it's okay to say I had problems with this, or this isn't working for me, or whatever. I'm happy to talk about it. There were lots of good grades on the exam. I'm almost done grading the written part. There's a few of you that don't have written grades yet. I just need to cross the T's and dot the I's, but you'll have written grades definitely by Wednesday or Wednesday afternoon. And the way we'll address questions on the exam is that if you have a question, you need to attend to office hours. So I'm not going to talk about the exam in class. You need to come to office hours and ask me directly. You should have the exam up on your computer so you can show me what the question is, because your numbered questions are not the same as my numbered questions based on how Canvas does exams. And so I'm happy to address any exam questions in office hours, not during class. Make sure you print off homework number 3 so you know what you have to learn this week. Make sure you're thinking about that. I will cover in the next 3 lectures all the things that you need to know for the homework, and you can turn it in on Friday afternoon as usual. And I think that's everything. Any questions? Okay, so exam number 2, you have a question? Okay, go ahead.
So are the 6 points from the portion, is that like extra points or not just separate?
No, the exam is out of 26, 20 multiple choice, 6 written. So you add your 2 scores together, divide by 26, and that's your score. Yes. Oh yeah, I'm working on the clicker. I just need to do some database stuff, so I'll update you on the clicker hopefully this week. Yeah, I just didn't get to it. Yep, that's on my list of things to do. Let's see. There was one more thing I was going to say. Oh, exam 2 is only going to cover the material in section 2. Now, you can't forget about molecular weight. You can't forget about addition polymerization. You know, you can't forget the easy stuff. You can't forget what styrene is. But exam 2 is going to test you on things that we cover from today up to the review section. I'll have another list of topics, just like I did a review set of slides for exam number 1. I'll have the same thing for exam number 2. And so, you know, you won't have to know a lot about Carruthers equation. You know, we hit Carruthers really hard, and we hit step growth really hard in exam number 1. That's going to be pretty well de-emphasized in exam number 2. However, the final is cumulative. And so, you know, you are past unit 1. We're going to focus on unit 2 now for exam number 2, but you can't forget the stuff like Carruthers and the things that we learned on molecular weight distribution in section 1, because that will come around again on the final. And remember, the final is a little bit longer than the usual exam, so I can put some more stuff in there. So the final is cumulative, but the exams are not, if that makes sense. All right. So to start off today, I wanted to introduce you to Dr. Hawkins. So Dr. Hawkins worked on some really interesting technology in this super interesting research institute called Bell Laboratories. So Bell Labs is one of the most famous scientific organizations in the history of the United States. There are so many good scientists that worked at Bell Labs, and it turns out that AT&T, the telephone company, set up Bell Labs to do research about telecommunications technology. So they invented the transistor there. They invented this cladding for cables. All sorts of cool electronic and polymer innovations came out of Bell Labs. And there's still famous scientists today that work at big universities that started at Bell Labs, like John Rogers and Jen Bao and others. So what's interesting about what Dr. Hawkins did is he worked on the polymer or the sheath for cables. So he worked on a new class of compounds that are basically the cladding, that rubber cladding on the outside of an Ethernet cable. That's what Dr. Hawkins invented. And so for that, he's in the National Inventors Hall of Fame. So now you know that there's one of those. And Dr. Hawkins received the most prestigious prize in the United States for scientists and engineers, which is the National Medal of Technology and Innovation. There are fewer recipients of that prize than there are Nobel Prize winners. They award Nobel Prizes every year in a bunch of different fields. They don't award this very often. And so Dr. Hawkins worked on some really important technology. So you're saying, well, you know, we've got wireless now. I'm not into cables. It turns out that big places like Facebook and Google and anyone who runs a data center is still really into cables, because this is what the back end of a data center looks like. So it's still all tied together with copper cables. There's some fiber optic and other things like that. But even though we don't have a lot of Ethernet cables around anymore, this is still a really important technology in data centers. And it turns out that it's a really important technology around the world. So most internet traffic is still carried on undersea cables. So satellites are too expensive. It's intermittent communication technology unless you have a really good constellation of satellites. And so most of the internet still runs through fiber optic cables that sit on the bottom of the ocean. And there are a lot of them out there. It's really amazing, and we can thank Dr. Hawkins for that. Yes?
So like how frequently are those replaced?
All the time. They're constantly working on them. Yeah. It turns out that, you know, countries are very interested in where other countries' undersea cables are. This is done sort of by public-private partnership, making sure these cables are put in. And so this is a really, really important network in the world, and folks are really interested in where all these cables are, how they're maintained, putting new ones in, et cetera, et cetera. All right. So anyway, there is your piece of history. So we've already covered a lot of what we're going to cover in this class on step growth. Remember, Carruthers was the key set of knowledge that we learned about step growth polymerizations and RA2, RB2 polymerizations, etc. And now we're going to focus on chain growth. And of course, we've got something like this, xn, p, x bar n, 1 over 1 minus p. So that all works as long as you're talking step growth. Now we're going to talk about chain growth, or you also know this as addition polymerization. So we're going to learn about all the different characteristics of addition polymerizations, including the mathematics of how those polymer chains grow and things like that. So in addition polymerizations, we're generally dealing with free radicals. And so you want to remember what a radical is. You want to remember the rules of radicals. And so when are radicals stable? When are radicals not stable? And you know from your chemistry classes that radicals, do they have a short lifetime or a long lifetime? How long do they stick around in general? Short. So radicals don't exist for a long time. And that's why we get polymer very quickly for addition polymerizations, because it turns out in addition to radicals having a short lifetime, they're really reacting. And so we talked about addition polymerization or chain polymerization as a chain reaction. Turns out it's a chain reaction of radicals. And so you get high molecular weight polymer quickly at low conversion. And then sort of the molecular weight plateaus as you go to higher and higher conversion. Now, remember what conversion means. It's the percentage or the fraction of monomer that's converted to polymer. So we can be at a conversion of 10%. We've only changed 10% of that monomer into polymer, and we still have high molecular weight in addition polymerization. In step growth, of course, it's other things that we don't need to talk about because we already have. Or we can have conversions of 90%. So 90% of the monomer has changed into polymer. We can still have high molecular weight. So you need to remember what's the definition of molecular weight based on the degree of polymerization versus what's the definition of conversion. And you can have high molecular weight at low conversion if you're doing addition polymerization. All right. So we talked about these types of monomers in the first unit. And so we're only going to be using carbon-carbon double bonds for the most part in this unit. And so they go by a little bit different names depending on exactly what they are, but we've already talked about vinyl monomers. Acryloyal monomers are fine. They just have this carbonyl next to the double bond. Styrene, you should just know that one. This one is called methyl methacrylate. And notice there are two meths in there, two meths in that name. The first methyl is this one right here. So that is the methyl for that group. Methacrylate is the name of this whole thing because there's another methyl group right here. So I'm going to make a little star here and a little star here. That's that one. So we'll talk about acrylates, we'll talk about methacrylates, we'll talk about vinyl monomers, but make sure when you're looking at these structures, you could say, okay, this part of the name goes to this functional group, and this part of the name goes to this functional group. That will help you try and think about what the names of these compounds are. Vinyl acetate, acrylamide, which we've already talked about a little bit. So you should have some of these monomers in your head. We're only going to study 10 or 15 of them. So it's going to be a lot like step growth polymerization, where there's some just key polymers that you should know. We'll have some key monomers that you should know, but you should always be looking for that double bond or that carbon-carbon double bond, and don't make any polymers going through the carbonyl, right? Just don't be tempted to do that. Okay, we've already talked about this. We've talked about arrow pushing and how addition polymerizations work. And so the upshot of this is that you have this thing called the active center. So the active center is the growing chain end. And remember what these squiggles mean. This is a polymer chain. So we have a polymer, polymer like this, although it's all bent up. And then right on the end of that polymer is a free radical that's sitting there ready to react. And that free radical on the growing chain end attacks a monomer that's just sitting in solution. So this looks like a monomer, right? And we decompose that double bond. So we take one electron, push it one way, one electron, push it the other way. And now we get a growing center. And we've added this monomer. Because if you count the carbons here, 1, 2, so we just had those 2 carbons on the growing chain end to start. We added carbon 3 and 4. We've got 1, 2, 3, 4. And now the active center is sitting on the new monomer, right, that we just added. This is really important It looks easy when I'm up here doing it, but make sure you can do this. Make sure you know how to move or propagate the active center to the next monomer when you add it. And we'll talk about all the little details. So this is where half arrows are really important. This is where being able to identify what the active center is, and then how to add that next monomer on. Yes?
So is there any possibility that it's kind of like, there's not going to be a new active center once it reacts?
We'll talk a lot about that. Yeah, we'll talk about what happens to the active center, because there's a bunch of different stuff that can happen. This is the easiest way to start. Any other questions? Yes.
So it has the homolytic and the combination. Is one more is one preferred over the other? It's like one more stable.
Well, notice that the homolytic cleavage and, well, this is not perfect, because you can, this is the monomer here, it goes to this, and then it goes right to here. This is the growing chain end. So this is, I didn't talk a lot about 1 and 2 because it's not a perfect diagram. This is overall reaction is much more important, but we'll fill this picture in as we go. Other questions? All right. So for free radical polymerization, which is chain growth, addition, all those terms still work. We're going to have a couple different flavors of chain growth and addition polymerization, but that's still the genre we're in. We've got 3 stages. So when you have monomer just sitting there, radicals are short-lived species, right? And you don't have like a bottle of radicals. And so you need to make radicals somehow, and that's called initiation. So the act of making a radical and starting the polymerization, you initiate the polymerization. It's called an initiator. You start the chain reaction of radicals. Propagation is adding monomer, monomer, monomer. So propagation is where you increase the molecular weight as you're adding monomer to that growing chain end. And then termination is when the radicals combine and you don't have an active center anymore. Because if you made one radical and it just grew and grew and grew, it would take that whole vat of monomers and make one chain out of it. And that's just not how it works. Since radicals are reactive, things can happen to them. The growing chain end is quenched or stops, and that's called termination. But make sure you know these terms and make sure you know where you are in the life cycle of a polymer. These are the scientific words that we're going to use to describe this process. And we're going to talk about chain transfer in a couple lectures. It's going to get more complicated than the first 3. All right, so we need to generate radicals with an initiator. And it turns out there's 2 important types of initiators in this class: peroxides, which has an O, single bond O. It turns out that's a pretty weak bond because oxygen is pretty electronegative, right? And so it wants to cleave that oxygen-oxygen bond to form 2 peroxy radicals. Azo compounds with that nitrogen double bond in the center. Turns out that nitrogen double bond really wants to be a nitrogen triple bond and be nitrogen gas. And then you get 2 R dots from that. So remember our nomenclature: anything with a dot is an unpaired electron, which is a radical, which is going to want to go find other electrons, right? And so we start to get radical initiation from initiators. Great. And there's some complicated stuff that happens, like benzophenone cleaves into 2 different radicals. You probably don't have to know that one except on homework. Benzoyl peroxide, you don't necessarily need to know what benzoyl is, but since it's a peroxide, you know it's got an oxygen single bond in the center of the molecule, and you get 2 radicals from that. Yes.
So do these initiators only work with air light, or can they just work on their own?
Oh, so this can work with heat. So delta is heat. H nu is light. And of course, heat, 0 degrees C still has temperature, right? So you can design different peroxides that cleave at different temperatures. It's actually a useful thing to do. So depending on the wavelength, depending on the temperature, you can get these initiators to generate radicals under certain conditions. All right. So once we have an initiator, so let's just take R dot as our initiator fragment, and we have this monomer, right? We're going to have lots of generic monomers that look like this. So this monomer is basically that thing, right? Double bond with some sort of R group, and in this case it's X, just so we don't have too many R's floating around. And so we can add the monomer in one of two ways. The initiator fragment, this radical, can attack this side. Well, let me get my arrows going here. So this guy can go here, and it can grab an electron from here, right? And then we go that way. Or we do the same reaction just on the other carbon of our monomer. And it turns out that by switching that monomer around, make sure you can see that we're attacking the unsubstituted carbon in mode 1, and we're attacking the substituted carbon in mode 2. You notice that the growing chain end is different once we add that monomer. So which one is more likely? Knowing the rules of radicals, do you expect mode 1 or mode 2 to be more likely? Chemical reactions tend to form the most stable products, right? You're looking for stability because that's how the universe works in terms of going downhill in energy. So what is the most stable product, mode 1 or mode 2? Go ahead.
Mode 2.
Why is mode 2 most stable?
Because it doesn't have a halogen, it has the 2 H's.
So what are the rules of radical stability? What's the least stable? Primary radicals. What's the most stable? Tertiary radicals. So it turns out that mode 1 is most likely because it's the most stable product. So whether it's a halogen or whether it's an R group, we'll talk about that in a second, that this is the correct product, that the growing chain end is almost always on the most substituted carbon. There might be some exceptions, we can go find those, but you want to make sure that the growing chain end has that substitution on, because this is a primary radical, right? Nothing to stabilize it, nothing else going on. And so that's the least stable radical that we know about right now. It turns out that there are some funny rules with halogens, but whether X is a halogen or R2, it turns out that that is still the most stable, and we'll talk about why. Even though halogens do destabilize radicals, you're right about that. So because this primary radical is so unstable, it's very unlikely to form. It can form when we make a polymer. There's billions and billions of chemical reactions. One is going to get goofed up, and we'll talk about that. But mode 1 is the most likely. All right. So get out your clickers. Let's see. C and D is what we're looking for. So mode 1 usually predominates in radical polymerization. Why is that the case? So the multiple choice questions might get a little trickier now that we're in exam 2. I didn't have a lot of all of these and none of these in exam 1, but there's no guarantee that that's going to continue. And so just like the clicker questions help you figure out how I'm going to ask questions, why do we get mode 1 mostly? Methylene carbon is less sterically hindered. That's true, right? There's less steric hindrance around this carbon And so that's looking pretty good, right? So that's not untrue. The product of mode 1 reaction is more stable. That's looking pretty good. That's what we just talked about. Mode 2 is more reversible, so you get a buildup of mode 1. Haven't talked about reversibility. That's probably not good. Probably not all of these. And so I think the correct answer is D. There we go. So it's really easy to attack this carbon, because remember what this monomer is looking like. That double bond is sticking out there, and that non-sterically hindered carbon or least substituted carbon is just sitting there ready for a reaction, right? And we talked about stability, and so A and B is a pretty good answer. All right, I'm going to stop the clicker. Okay. So given this, now we need to think about adding the second monomer, because remember, we've only taken the initiator and added one monomer unit. So what's the end group so far? We have a growing chain end, right? We have this thing, which is going to add another monomer. And then the end group of this polymer is going to be the initiator fragment that we started with, whatever that is, right? So that's one end of the polymer. So we talked a little bit about end groups in step growth, or in step growth polymerization last exam. We'll talk a little bit about end groups in chain growth as well. All right, now propagation. And the key for propagation is that you have to remember you're adding one monomer at a time. And so even though I say it's fast, even though it's a chain reaction, chemical reactions can be fast, but they proceed based on some rules. And so the rule that we're mostly going to have is head to tail addition. And you can memorize head to tail, or you can say, this is my growing chain end, and I know the head is going to be the most substituted carbon. And I know that this next monomer is going to insert like this because that methylene carbon is not very stable, and I'm going to make the same growing chain end again. So this is on the head. And so the monomer head and tail, the way to keep it sorted out, the head is the most substituted carbon. And the tail is the least substituted, and that's usually where the radical attacks, because it's the least sterically hindered. All right, and you just have to bear with the head and tail nomenclature, because this is actually how it's written in all the books. The people who invented polymer science just decided to do it that way. And so here's the arrow pushing right here for head to tail addition. It turns out that you can have a head-to-head addition. So this is the most stable growing chain end, right? And if that monomer that we're going to add is turned around the other way, we're adding a head plus a head, and we get head-to-head addition. And then where does the growing chain end up with a head-to-head addition? On the tail of that growing chain end, right? That looks a lot different than our growing chain end right here. So head-to-head addition is a problem, and it's rare, but it still happens. Yes?
Could you just explain once again why the head more substituted than tail?
Because that's the convention. So the rule is that the head is always the most substituted carbon, because that's where the stable radical sits.
All right.
Yeah, that is just how it's done. And so when you look at a monomer for the very first time, I mean, we could go back to our monomers, and knowing the convention that the most substituted carbon is always the head. Here's the head here, here's the tail here, here's the tail here. This is the head carbon. Here's the head carbon, here's the tail. Oh, there's lots of stuff going on here, but this is still the tail, and this carbon is still the head. So you should be able to identify the head and the tail of the monomer very easily. And the only way we call it, or the only reason why we call it head and tail, is that we want to think about these types of defects in the polymer chain. So that's called a head-to-head defect. And of course, if we have tail-to-tail addition, this is called a tail-to-tail defect. And so when they were inventing a lot of these addition polymers, they said, okay, we figured out that mostly things are head-to-tail addition. That's the usual rule of things. But it turns out if you have really sterically hindered groups right here, head-to-head addition can give you a weak spot in the chain. That you can actually break that bond thermally and other things like that. And a lot of times, once you have a tail as your growing chain end, you get tail-to-tail addition right away because, of course, inserting a monomer like this is the preferred way to make the next one. So once you get a mistake in the chain, once you get a head-to-head addition, it's usually followed up exactly by a tail-to-tail addition so you can get back on track with head-tail, head-tail, head-tail. Yes?
So does that head-to-head or tail-to-tail addition kind of imply like some sort of impurity within the actual substance? Or
Well, it's not an impurity, we call it a defect. Yeah. So it's a chain architecture defect because the bonds are different than what we would expect from a repeat unit. So it's not an impurity because it's all the same types of atoms, right? We call it a defect. So you'll hear me say head-to-head defect, and that's what it means. Head-to-head linkage, head-to-head reaction, tail-to-tail defect, those things. It's basically a mistake in the regular order of head-to-tail addition. So the only thing you really need to know on this slide is that the most substituted carbon is the head. And so once you can identify the head of a monomer and the tail, you can build up a polymer chain. All right, you can get out your clickers. All right, which do you think is more likely to happen? Head to tail, head to head, or tail to tail, or are they all the same? This one should be easy. And even if you weren't listening to me on the last slide, you notice that here, this is unlikely. This is unlikely, right? So when we have that radical sitting on the tail, that's not very likely because it's not a very stable configuration. But here we have radical on the head. Here, the growing chain end is on the head. So just by a most likely scenario, of course, head to tail addition is most likely. Oh. And that's what we have right there. So that's very simple, and it looks really easy when I've drawn it up here for you, but this is one thing you go take home, practice, make sure you know when you have styrene, which is the head, which is the tail, how does it go in? The easy way not to screw this up, of course, is to write all the hydrogens. You don't have to write the hydrogens on the aromatic ring if you don't want to, but this is a good way to think about, okay, how do I start to write some of these structures? Because I know you practiced your polyesters and your nylon 6,6s, and I saw some good chemical structures on the exam. You want to do the same thing for these. Make sure you can make chains out of them. Make sure you know what the repeat units are. Make sure you know what head to tail addition is, all of that stuff. So this is just something you're going to have to study. All right, you can keep your clickers out. What type of linkage is this? First of all, what polymer is this? Does anyone know? Let's look at the repeat unit. 1, 2, 3 carbons. Does anyone know what that's called?
Polypropylene?
Polypropylene, and this is the monomer right here. 1, 2, 3 carbons, or CH2, CH, CH3. Great. Based on that knowledge, now you know what the head and what the tail of the monomer is. So what's the linkage in this polymer? Right in the center, right here. So we know this is the tail. This is the head. And so you've got 2 methyl groups right next to one another. There we go. Need about 52. I've seen 54 up there. Oh, losing a couple people. All right. So that's a head-to-head linkage. So when you see, well, most of the monomers that we're going to deal with are of this form, right? And so when you have those two R groups right next to one another, that means you have a head-to-head linkage because the head of one monomer where that R group sits is reacting with the head of another one. So, you know, this repeat unit just tells us what the polymer is. It's really easy to see what the monomer is when we have the parentheses around it, right? We're in addition polymerization, and so we don't have to get too fancy with thinking about what the chemistry is. It's really easy to know it's an addition polymer because there's only two backbone carbons in the repeat unit, right? Head, tail, carbon 1, carbon 2. That's a dead giveaway for addition polymers. And so, you know, you have to count a little carefully, but once you have those two head groups together, you know that that's a head-to-head addition. Any questions? All right, again, since we're changing classes of polymers, this is a really good idea to go draw those things out this week. Think about how these monomers are working and think about how they might go together. So initially we started off saying, well, if it's a halogen, could it be destabilized? And that's true because halogens do destabilize radicals, but it turns out that this, so for this vinyl fluoride, right? It's a vinyl bond with a fluorine connected to it as an R group. This is still the tail because it's the least substituted carbon. This is still the head. But if you look at the space filling model for this molecule, so this is all the orbitals or the most likely orbitals. This is what the monomer actually looks like. So this is carbon. This is carbon. This is fluorine. This little guy is hydrogen. Because remember, there are not many electrons around hydrogen. That means they're small. There's plenty of electrons around carbon and fluorine. And so sterically, there's a lot of places that we can have reactions on the tail carbon. This is the head carbon. And so it's just more likely that a reaction will happen on the tail. So, you know, formally, the halogen does destabilize the radical, but 90% of linkages are still head to tail, even if that radical is destabilized. So that's the one exception that we can think about. So there is no exception to the head to tail linkage being more prevalent. This is just the one example of a destabilized radical still being the growing chain end on the head of the monomer. So there's nothing to memorize because it's always the same. Tail to head is most likely, and you know the reasons why now. Any questions? Okay. Last thing we have is the last easy part we have is termination. So remember, initiation, you make the radicals in the first place. Propagation, you're adding monomers, and then termination, the radicals have to die sooner or later to get whatever molecular weight you're interested in. And so there's two modes of termination. And so these are important because we're going to talk about both types of termination in detail. And so it just so happens that if two growing chain ends find each other in solution, you get termination by combination. And what linkage do you have right here? What's that called? Head-to-head defect. So that's a signature now of combination. Two growing chain ends are in solution. There's not many of them, right? Because the concentration of radicals is not very high. But it does happen because there's lots of reactions that happen when we're making polymers. And so the signature of termination by combination is a head-to-head defect. Also, what has happened to the molecular weight of our polymer? What's the molecular weight of this guy right here? X minus 1 times M0, right? Whatever that is. And so we get that certain degree of polymerization, or the degree of polymerization eventually is going to be X. We've just drawn out the repeat unit. Degree of polymerization here is going to be Y. So we take that Y minus 1 plus one more monomer. That's going to be Y. So we have X bar N equals X and X bar N equals Y. What is the X bar N of that polymer? It's not a secret. X plus Y. So you haven't extended the molecular weight by one monomer unit, right? During propagation, it's X bar N plus 1, X bar N plus 1. You know, you're adding one monomer at a time. Here, you're taking two polymer chunks. This guy, X minus 1 or X, whatever we want to call it. This guy, Y minus 1 or Y, and they combine and you get one mega chain that's the sum of those two chains. So your molecular weight can increase drastically with one reaction. So that's another signature of termination by combination, is you get some high molecular weight polymer because you're taking two chains and reacting them together. So you've got head-to-head defect, and you've got high molecular weight chain. So the head-to-head defect is easy to see, right? Because that, we just talked about that. You should be able to say, okay, I've got head reacting with head. I get that. High molecular weight chain, you know, I'll show you a different scenario in a second, but you're taking two polymers and adding them together and you get one chain from that. So that's a signature of termination by combination. All right. The other termination mechanism is termination by disproportionation. And, you know, there's a lot of arrow pushing on this slide, but basically all you need to know is you wind up with two dead chain ends and a double bond. They call it disproportionation because you see this hydrogen goes all the way back over here. And so in order to get rid of that radical, right, you need to have 4 bonds to carbon somehow. And so we've got carbon adds an H, and the proton, the hydrogen, came from the other molecule. It disproportionated. And then in order to complete the octet for those carbons, you need a double bond right there. So that's hard. There's a lot of stuff going on here, but you could say that disproportionation is more complicated to spell than combination. So disproportionation is a complicated one, and I wind up with a double bond somewhere. That's complicated. So that's disproportionation. And notice no molecular, no molecular weight increase. So you have your X bar ends of the two growing chains. They terminate by disproportionation, and the only signature that you really have is this double bond. And notice that you're taking vinyl bonds, right? Or in this case, X, sorry about that. And you're opening up all those double bonds. And so even though you start with double bonds in your monomer, the polymer doesn't have any double bonds in it, right? And so if you have this type of termination, all of a sudden these double bonds start popping up again, and you can see them in NMR or another chemical analysis technique. So when you start to have lots of double bonds on the chain end, you say, termination by disproportionation is dominating. Yes?
So Are those both the products that will be presented, like, those two, like the actual left side and the right side? Are those like two different products, or are they just like either or is that just one?
No, this is A, the top line is A plus B, and you get, I mean, this is basically a chemical reaction. So these are the reactants and these are the products. So you have two reactants, right? Two growing chain ends, and you get two product molecules from that. So this is not either or, this all has to happen. Just like this, we start off with two growing chains, A plus B equals C, one molecule. So we go from two molecules in the reactants to one molecule in the products. Disproportionation, we go from two molecules in the reactants to two molecules in the products. Yes.
As far as the two types of termination, what determines which one occurs?
That's right. So you need some extra information to figure out what's happening. So based on the conditions and based on the monomers or based on the information that I tell you in the problem, you'll get some hints as to what's happening. So I might tell you disproportionation dominates, and then you'll answer the question. Or I might tell you combination dominates, and you'll answer the problem. Or I might tell you there's so many moles of double bonds, what happened? So there will be some hints in the problem as to what's going on. Yeah. Okay, so these are worth studying, right? So if you're like, I got addition polymerization, I know what's going on with free radicals, that's not a big deal. This stuff is a little bit harder. And I'm going to ask you a lot of questions about termination by combination and termination by disproportionation. So make sure you're ready for those. All right, yeah, so here are some similarities and differences. One key difference is that you have only one chain when we combine termination by combination, which means 1 mole of polymer, right? I haven't told you what the molecular weight is, but 1 molecule is equated to 1 mole because it's still a number. And here we've got 2 moles of active center, and we get 2 moles of polymer chains at the end. That's a key signature along with this double bond. All right, and this is just the review. So we're going to move on a little bit because we did miss a lecture. And so remember, we are on lecture 10 in section 2. If you can't find them in the OneDrive, go back and look. And we will go on to note set 11. All right. So remember how we drew this curve? And I said for addition polymerization, we didn't have an equation for that curve, right? We've got Carruthers for step growth. But this type of curve is called a kinetic curve. And it's going to tell us how quickly we get polymer to form in this process. And so we're going to talk about the kinetics of this active chain center adding monomers, because the faster the polymer grows, the steeper that curve is, right? The more buildup of polymer we get as a function of time. So the one thing that can happen in this whole process is that the radical can get sidetracked by this thing called a chain transfer agent. Now, let me show you one more thing here. Does anyone remember what this, where does that R group come from? What's that on the chain end? Yeah.
The initiator.
The initiator fragment, right? Because in addition polymerization or in radical polymerization, where you're initiating radicals with some sort of initiator, that's the start of the chain. And then the end of the chain depends on what type of termination we have. That's really interesting. It turns out that this growing chain end can react with other stuff, and we're going to call this a chain transfer agent. It's just abbreviated T-A. That doesn't stand for any specific atoms, but it's a chain transfer agent with a covalent bond in it. And if you think about this, we can get a reaction with our chain transfer agent where now we terminate the chain with T, not a real thing, just a fragment of the chain transfer agent. And now we have a new radical right there that can propagate, that can do other stuff. So all a chain transfer agent does is it moves the growing chain end from a polymer, right? This is a growing chain end or an active center on a polymer. It moves the radical off of that polymer to something else. And that something else is usually a small molecular weight compound, like another monomer, solvent. You can have chain transfer to initiator. But the thing about a chain transfer agent is that the chain does not die. You don't have termination, right? This is not termination by combination. This is not termination by disproportionation, but you move that active center somewhere else, and that's called chain transfer. And so what's the molecular weight of A? Is it lower or higher than the polymer usually? Lower. So you move the active center to a lower molecular weight polymer, or a lower molecular weight compound that slows down making long polymers. So chain transfer is a way that you can limit molecular weight, and we'll talk about that on Wednesday. So thank you very much. Remember your PLAs and remember your homework. See you on Wednesday.